What's up? What's up? It's your man, Jimmy Chan. All right, so with 4.1 and 4.2, we're talking about scatter diagrams and correlation. So first, let's talk about this response variable versus the explanatory or predictor variable. Okay, so the predictor variable is actually the so-called X value. It's independent. It's going to predict, right, what's going to happen, and the response variable is your so-called outcome, which is your Y. Oops, that doesn't look red. Your Y value. Okay. So a scatter diagram is basically you're going to get a bunch of points that when you graph them, it's going to be scattered. So if we look at this, what we will see is that what we can do is go ahead and graph this in Desmos, and I will also show you guys how to do it in the TI-84 as well. All right. So here in Desmos, in the graphing calculator, first, you would go ahead and hit the plus sign right here, okay? And then you will select table, all right? So we got to hit the plus sign, and we want to hit table. That's actually okay. When we do that, what we're going to do then is going to enter, we're going to get a table like this, with obviously nothing, so we're going to enter the data points in here so it looks something like this. All right, you can certainly enter column 1 first, then enter column 2, just like if it was in here. And I'll get something that looks like this. So the problem is that when we look at this, it doesn't look linear, but it really is, right? Because in real life, we can't be exactly the same. Like, unless it's a machine, even then, it's gonna look more like dots here, like it's in the row. So in other words, what we put in is we know exactly what's coming out, which in nature, that is not necessarily the case. And this is talking about club head speed in golf versus the distance of the ball. So that is not necessarily gonna be true as well, because all depends on how well we hit the ball, right? So 100 miles an hour with the club head speed might get one person 257, but if it was Tiger Woods, that's a very slow swing for him, but he might also get like 300 yards just from that, and then when he increases, he might go further. So because he can hit the ball more better, more gooder than anybody else, right? It's going to hit the center of the face of the club better than anybody else. If we don't hit it to the center of the face, we're going to lose distance, okay? So that's why in human nature is not gonna be the best so-called prediction, all right? So from there, because when you look at this first glance and not know that we're in statistics, you might say, well, that doesn't look very linear because I can't draw a straight line through all of these points. But in nature, naturally, we wouldn't be able to draw a line through all of them. So we would do a best fit line. But if you look at this, and here's the space that you're going to see the steps for the TI-84. So what you're going to see is more something like this, right? Where a so-called linear would be a little scattered, but you can see that every single time the club head speed increases, the distance does increase, right? And that would be positively associated because we're going to have a positive slope, right? And where this is linear and this is really a negative slope, so it'll be negatively associated, but they're both going to be linear. Where when it comes to this, it's nonlinear because it looks more like a quadratic, and this is looking more like a cubic, which that is for another day. All right. And then there is something like this, where is it a line this way? Is it a line this way? Is it a flat line? Is it, can I draw something here that's quadratic, either way, or cubic? It all seems kind of the same. So this would be considered there's zero relation whatsoever. Okay. So with that being said, what we can do is on the Desmos, we can actually enter in the next segment this piece right here, right? So in that segment, I know that's a little bit smaller, so I made it bigger right here. Let's put it right here so that you guys can see exactly what that says, okay? So what do we have here? What we have, this is gonna do that to me, isn't it? Okay, so let's be nice. Let's just do this. I can't even move this above. Let's do this. Let's move this in a little bit. All right, and let's put this over here like so. Because what's going to happen is that this one, every time I tap on this one, it's going to cover everything up. So what does these numbers mean? So what these numbers mean is that I'm writing in here y1 because this is saying y1 right here, and x1 because this is saying x1. So this equation here that I'm putting in has to involve, I want these numbers to be involved. So that's why I say, okay, I want the list that's labeled as y1, the list that's labeled as x sub 1. And I know that y equals mx plus b is my equation of my line, but instead of saying equals, I'm going to say is approximately. All right, so what it will come out to is that you're going to see a correlation coefficient, which we'll talk about in a little bit. We're going to see the slope, and we're also going to see the y-intercept. Okay, so we're going to see both of those things right there. So in other words, this line right here, actually, let's go ahead and change this color. Plus, use a dropper. Let's put it right there. Okay, done. So this line right here is going to be y is equal to 3.166x plus, or actually minus 55.797. So I have an equation for this line that I've drawn, that it has drawn. I didn't draw it. It has drawn, right? And then we'll talk about the correlation coefficient in a little bit. So that is exactly what that is. This is what this is giving me right here, okay? So look at this. So the correlation coefficient, as we're saying, this is 0.9387. So let me go and write that down. R is equal to 0.9387, okay? So let's keep this in mind as we're going through the go-through, all right? So it says, the properties of linear correlation coefficient. The linear correlation coefficient is always between -1 and 1, right? If it's a positive 1, then it's a perfect positive linear relation. If it's negative, it's a perfect negative linear. If it gets close to positive 1, is a very strong evidence of positive relation. And if it's negative, is a very strong evidence of a negative relation. If it's close to 0, then there is no evidence of the existence of a linear relation. Okay, we just call that nonlinear. And then the linear correlation coefficient is unitless. The correlation coefficient is not resistant. Therefore, an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient. Okay? All right, so let me go ahead and take this and bring it down here. All right? So if you look at this, what do you see? What you see is, like they said, if it's 1, it's perfect. Exactly. Every single time you swing that club, that exact speed, you get that exact distance, right? Where if it's -1, it's perfectly negative relation, all right? But notice all of this here, the difference between this one and this one, okay? This is strong positive because it's close to 1. But if you notice, if I was to draw a line in here, let's say I draw a line right here, right? The separation of the points from this red line is minimal, right? While if I put it over here, then you can see that the separation is a lot more. And that's why the correlation coefficient gets lower, all right? So, and then, and negative, it just means that the line is more in this direction, right? But again, if you notice the difference between here versus here, the numbers more, the data points are all more spread out. That's why it's going to be lower towards 0, where this is going to be closer to -1, okay, or further away from 0, right? However, as we get closer and closer to 0 for our correlation coefficient, this is what happens. It gets all over the place. I don't know what line to draw. Is that the right line? Is that the right line, right? I'm not really sure. Now, if you get to this, same thing. Because again, there's no line to be drawn. Do I draw this line or do I draw this line? Neither one of them are really right. That's the reason why their correlation coefficient would be closer to 0. All right. So how do we find correlation coefficient by hand? Man, this was much easier, wasn't it? Just to type it in. All right. So by hand, just so that you guys feel blessed, is that by hand, you will actually have to do this right here. So you'll have to make a table, right, of all the x's and find the mean of the x's and standard deviation of the x's and actually do all of that. And then do it for the y as well, multiply the two, and then summarize all of them. And then divide by n-1, which the n is really how many points we have, which in this case, luckily, is only 1, 2, 3, 4, 5, 6, 7, 8. So it's not as bad, but it's still plenty, right? 8 is still plenty. So be hopeful that we have calculators that can actually do that for us, okay? However, we do need a test for linear relation. So if the absolute value of the correlation R, correlation coefficient R, is greater than the critical value, we say a linear relation does exist between two variables. All right, so I just said that we had so-called, actually I should change the color of this since that part is red. Let's change it to purple. So we had 8, right? So n was equal to 8 because we had 8 pieces of data point right here. So let me go back to it again. So again, 1, 2, 3, 4, 5, 6, 7, 8. All right. So, and here's the thing. When you type this in, right, y is approximately, it will say right here that how many data points there are. And then it kind of goes away once you finish it. But it will tell you how many points there are. Okay. So if you pay attention to it, you will see that. All right. So here is the critical value for correlation coefficient. So if you look at this, I have n equals 8 right here. And it has a critical value of 0.707. But my R is this. So since this is greater, let me do it this way. Let me bring it over here. Since this is greater than 0.707, then what that tells me, based on what I'm saying right here, is that a linear relation exists. Now, if this R value that we got, or the correlation coefficient that we got, is less than this, then no, there is no linear relation occurring, okay? And that's even though if it's this right here. And the biggest example would be, hey, what if we had only 3 points, right? If I only had 3 points, how am I supposed to draw a line through, and say it's linear or not linear, right? So what will happen is that because of that reason, that's why you see that their critical value for 3 points is really, really high, because you got to be pretty darn perfect to know that it is linear, right? Those 3 points better be like right in line with each other for it to be absolutely linear, where I can actually draw a line that will actually go through all 3 points. So we better be, those 3 points better be pretty darn perfect, all right? And that is it for now. I hope that answers your questions. Anything else, let me know. See ya. Bye.